Okay, are you able to see my full screen and hear me?
Yes, sir.
Okay, good. So let's begin. Yeah, so last time we were talking about the NLR, and by studying the NLR of many galaxies, it has become clear that there is a correlation between the strength of NLR lines and the bulge absolute magnitude or bulge luminosity. Right. So what is shown here on the x-axis is the log of the O3 line strength and line width actually, and the mass of the bulge. Now, what does this indicate? See, remember the NLR is a feature of the something happening very close to the supermassive black hole, and the bulge is a kiloparsec scale object. But again, this is not surprising because remember, we've seen other correlations of this kind. For example, most famously, we've seen a correlation between the black hole mass and the bulge mass, and the velocity dispersion in the central region and the bulge mass, and so on. NLR line widths are indeed correlated with the host galaxy bulge luminosity, and therefore through the bulge gravitational potential. This indicates that the NLR widths are not necessarily reflecting the gravitational potential of the SMPH alone, but the gravitational potential of the inner part of the galaxy, meaning from the attraction from other stars which are lying within the NLR region. They'll also feel the potential from that. So this is not, again, not surprising because remember we said that the NLR region can be quite large, okay, of many parsecs, unlike the other regions which are very small sub-parsecs. This could be going up to 100 parsec or 200 parsecs or so. And because of that, it's going to feel the potential of the stars as well as the black hole. AGNs with powerful radio jets lie off the correlation, having larger widths than expected. And this we know is likely happening because the AGN jets are transferring energy to the narrow line region, excess energy beyond the energy that they are already getting through the photons emerging from the accretion disk. And because of that, this extra energy is throwing off the correlation. Otherwise, it's quite tight. There can be some non-virial components to the velocities, such as the shock interactions between the radio jets and the NLR gas. So remember, the NLR gas is receiving energy from photons in the accretion disk. It is also receiving energy because of shock compressions, shock interactions between the jet and the NLR gas. Okay, so before we go on, I would just like to try and fix a date for the seminar. So I had asked Swarnim to find out what the dates are, or Manish, I don't remember, one of you. And so I got the email. So I believe Ruta's exam is scheduled for 22nd of June, and Shriyanand had not scheduled the test yet. So then what I did was I sent an email to Shriyanand and asked him whether what are his dates. So he said, you schedule first, and then he will schedule his date around that. So now we need to try and fix a date for the seminar. So you are having your Astrotechnics 2 final exam on 22nd. So shall I propose something like 29th, or do you want to finish it off the same week? How do you want to do it? Right.
29 is fine for me. 29 is fine for me.
And then Shriyanand's exam can be in between, or it can be later. I don't know.
Sir, he said he's not sure about taking the exam. He is considering an additional assignment in place of exam. So
Okay. Okay. So in that case, we don't have to worry too much about it. So shall I just say 29th for the seminar?
yes, sir, I think it's fine.
Yeah. So 29th is a Tuesday. And given that we have of the order of 15 people, it's going to be a fairly long drawn affair, right? Even with only 20 minutes per person, we can do 3 per hour. And so we cannot do more than 9 or so in one sitting. And then, so we will probably do most of them in the morning, and then a little bit 3, 4, 5 people in the post lunch session. So I will propose starting at 9:30 a.m. on 29th of June. Is that okay with everyone?
Yes, sir.
Yeah. So I assume if anybody has any objections with the date, see, time can always be moved around if we have to. But if anybody has a problem with the date, please please send me an email or please speak up now. Okay. Otherwise, I'm going to assume that it's 29th, and I will later today I will send out an email announcing the date for the seminar as the 29th of June, which is a Tuesday. Okay. Right. One small announcement. This is only relevant for students at NCRA. The students from NCRA taking this course will soon have to take up 2 3-month-long research projects under 2 different guides. So one of the students from NCRA has already spoken to me regarding a project. But if there is anyone else from NCRA who is interested in doing a project with me, please get in touch by email. And I encourage you to look at my research interests, which are described on the page given here on my homepage. And there you'll be able to see what the various areas I work on. And as I've already said before, I work partially on AGN, active galaxies, but I also do a lot of work on star-forming galaxies and other normal galaxies. Okay. Right. So now we will shift to the one component that we have not talked about in detail so far, which is the dusty torus. Right. So in the unified scheme, we have said that the optical spectral differences that you see between type 1 and type 2 AGN are often due to an orientation dependent obscuration by geometrically thick and also optically thick structure, which we refer to as the torus. Okay. Now the torus sort of implies that it is torus shaped, as we shall see in a few minutes. That picture is probably wrong. One should not think of a Meduvada shaped object surrounding the central engine. It's not like that. It's not so simple. It's much more, the structure is more complicated than we originally imagined in the model. Nevertheless, there is some symmetry to it, and one assumes that the cylindrical symmetry will be maintained, at least in a statistical sense, right? It must have a large height. It can't be very thin, geometrically thin like the accretion disk. It must have some height so that at least at low enough luminosities, the majority of AGNs are obscured by the torus. What does the torus consist of? We've said, we've claimed that it consists of dust, and that is correct. But remember, the torus is not pure dust. The torus is a mix of dust and gas. The gas may be in the atomic phase, atomic hydrogen, for example, or it could also be molecular gas in parts of the torus which are where the surrounding dust and gas effectively shields the inner gas from the strong radiation from the accretion disk. In that case, you could have small amounts of molecular gas as well. In fact, such molecular gas has been detected recently with a telescope called ALMA, the Atacama Large Millimeter Array. The dust causes naturally large extinctions in the optical and UV, and sometimes even in the near infrared. Normally, in the near infrared, the extinction is much less than the optical. But if the optical and UV extinction is extremely high, then even in the near infrared, the AGN could become undetectable. Now we've made a lot of observations of these tori, and we've come to the conclusion that there seem to be a lot of variations in both the covering factor and the geometry of the torus, which means by geometry, one means it still preserves cylindrical symmetry, but what is the inner limit which is set by the dust sublimation radius? That's okay. But what is the outer radius? We don't know. Is it a clean sort of break, or is there a smooth merging into the interstellar medium? All of those things were unknown, but using observations with X-ray telescopes and also observations with near infrared and mid infrared telescopes, one has been able to gain a lot of insights into the structure of the torus. Now, remember, the torus receives photons from the accretion disk, which are all the way from sort of very hard UV photons to optical photons, right? These, including UV photons, of course. These photons, when they emerge from the accretion disk, when they hit the torus, some of them may be absorbed. And when they are absorbed, that will heat the dust in the torus, which will then re-radiate it thermally, like a black body or a gray body at the different temperatures, and give you emission typically detectable in the near infrared and mid infrared bands. A small fraction of the photons may also pass through. And we shall see in a minute why we feel that there are photons that are passing through. Because if it's an optically thick torus, there shouldn't be anything passing through. The third thing that can happen is there can be reflections. Okay, the reflections can happen, as we saw, from dust-dominated nebulae. Reflections can also occur in less dusty, from gaseous nebulae as well. So some part of light from the accretion disk could get reflected from the torus. The torus then acts like a mirror kind of structure, and then it will be able to reach us. The fourth possibility is that it can be scattered. And this, of course, also happens. Scattering happens in the clouds, but scattering also happens at the edges of the torus. And therefore, when you get light from the torus, you have to be conscious of the fact that the photons you receive are a combination of processing as has been described here. So if you look at the X-ray opacity of the gas, the X-ray opacity is strongly energy dependent, and high energy X-rays can in many cases pierce through the torus. So this is also something quite important to remember, right? That the hard X-rays can pierce through the torus. Now, since hard X-rays can pierce through the torus and soft X-rays cannot, it allows us to estimate the column density of the torus. And people have made estimates for various AGN, obscured AGN, and they've found values between 10⁻22 to 10 raised to 24 per centimeter square for the column densities. Some type 2 AGNs have column densities much higher than this number, very large column densities. There, even the higher energy, meaning the hard X-rays, cannot penetrate through. And such AGNs are referred to as Compton thick AGNs. So there are some tori where even hard X-rays cannot penetrate through. So here is an example. Here is an Xray spectrum. Don't bother about the various dotted and dashed lines, etc. Just focus on the data points which are indicated by the error bars. Okay, so there is one data point here, one data point here, and so on. Okay, I have to start the laser pointer. Right. So just focus on the data points which are here, 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 and a high number of data points that have been obtained here for a obscured type 2 AGN NGC 588. Now, how can we measure the size of the torus? We can measure the size of the torus the same way we tried to measure the size of the broadline region, by using the dust, using reverberation mapping techniques, this time for the dust, right? And wait for, assume that the V band emission is coming mostly from the inner part, from the accretion disk region, and the K band light is coming mostly from the torus, right? If you, under that assumption, you can calculate the delay between the V band and the K band, and that can be used to measure size. We also have the temperature profile of the accretion disk, with which you can estimate at what distance the temperature will drop to about 2000 Kelvin, which is the temperature at which dust sublimes. So that also gives you an independent measure of the inner radius of the disk. One can also try to image the torus directly, okay? And in order to do that, you have to do interferometry in the near infrared and mid infrared bands. So remember the kind of resolution that you get with separations of 10,000 kilometers, okay, which is 10 raised to 7 meters, you can get with an optical interferometer with a separation of 10 meters. Okay, and of course, the separation between the Keck telescopes and the VLT interferometer telescopes is larger, and therefore you can get VLBI type resolutions with in the near infrared and mid infrared bands. Why do you choose near infrared and mid infrared? Because that's where dust is supposed to emit strongly. So using the optical telescopes like the Keck and the VLT, it has been possible to do interferometry in these infrared bands and try to directly image the emission from the torus. Using all of these sort of size measurements, it seems that the size of the torus scales with luminosity. More luminous AGN have a larger torus, but it doesn't scale linearly. It's sublinear. It goes as the square root of the luminosity. The inner edge of the torus has been found to be typically at about 3 times the broadline radius for H beta that was determined by reverberation mapping. So the size, the inner edge of the torus is the distance from the AGN from the black hole is roughly comparable to the distance to the H beta broadline clouds. So inner edge of the torus may also define, therefore, for you roughly what is the size of the broadline clouds. So the broadline clouds are not very large in extent. So here is a figure,
Sir?
which, yeah.
So the inner edge of the torus, does it coincide with the outer edge of the accretion disk?
Yes, effectively, because remember the accretion disk falls off in temperature, right? And therefore, you will have that kind of scaling also, but it need not be perfect. Remember, the torus cannot intrude into a region where the temperature is higher than 2000 Kelvin. That's the, but the torus can go out. I mean, there is no reason to claim that the torus will be exactly where the accretion disk ends. The torus could be a little bit further out, right? So it only sets a limit, the size of the accretion disk.
And the broad line region is only in the central part of the accretion disk or all over the accretion disk?
The broad line region is a sort of, has a spherical symmetry about the central AGN. So the broad line clouds are found above the accretion disk, below the accretion disk, in a more or less spherical kind of arrangement about the central AGN. So the main difference will be the broadline clouds have more or less spherical symmetry. The torus has cylindrical symmetry, and the narrow line clouds, as we already saw, can be thought of as having a conical symmetry. They emerge in two cones, like we saw last time. Okay, so here is a figure which shows various measurements made for the size of the torus against the bolometric luminosity of the AGN. And various techniques, various data points represent measurements with different techniques, either interferometry with these optical telescopes like Keck and VLT, or reverberation mapping techniques between, let's say, the V-band flux and the K-band flux coming from the torus. So you basically, what you're saying is that the slope of this line, okay, will give you a scaling relation corresponding to L raised to 0.5 for the size.
Hello, sir.
Yeah.
Sir, in the x-axis, it is written as bolometric luminosity, but the observations are only made in mid-infrared or near-infrared. So how they decided?
No, they determine the bolometric luminosity of the AGN separately, not through these interferometric observations. Right? So the AGN is studied in the usual way. We have its broadband spectrum, etc., etc. We can measure it. And if it's a type 2 AGN, you have to make all kinds of corrections for the bolometric luminosity. So don't take these numbers very, very seriously. The error bars can be quite large. And so, but roughly, very roughly, if definitely if the AGN is more luminous, the size of the torus is bigger. That's all. Okay.
What is the half-light radius?
Half-light radius is the radius. Suppose you're measuring anything, right? You'll find that it is bright in certain portions and it fades out outside. Like the most easy way of defining half-light radius is for an elliptical galaxy, right? Elliptical galaxy is brightest at the center, and as you go out, it becomes fainter and fainter, right? Now, what you can do is you can model the profile, the light profile of the elliptical galaxy, right? And fit it and assume the elliptical galaxy extends to infinity. So then if you integrate over the light profile, integrate over radius, you will get the total light from the galaxy. Then you find out at what radius half of that total light is contained. And that you can do just with photometry, and that gives you an estimate of the size of the galaxy, because you don't want the size to change depending on how sensitive your observation is. So if you take a 5-minute exposure of an elliptical galaxy, you'll see it of a certain size. If you take a 10-minute exposure, it will grow larger. If you take a 20-minute exposure, it's even larger because you're seeing fainter and fainter parts of the galaxy, correct? you don't want the size to change depending on your exposure time. So to avoid that, people use this technique wherein you use half the total light, the radius which contains half the total light of the galaxy.
But,
Of course, as you detect more light, you will that may change, but that's a very small amount of light outside. Yeah.
in some cases, we are finding out the radius using reverberation mapping, right?
Yes.
Not photometry.
Not photometry.
So
So
that is
then
actually-
they must have some kind of scaling to convert the reverberation mapping size measurement, which is going to give you a single C delta T kind of value for the distance. They must have some kind of thing relation to scale this and map this onto a half-light radius.
Yeah.
Yeah. Okay, I mean, this is from the paper. If you want to do more, know more, just look at this this paper by Bulge et al. Okay, now we ask an important question, which is the torus solid or is it clumpy? Remember, we asked the reverse question in the case of broadline clouds. We said that we assume that these are distinct cloud entities, and then we took data and that revealed that there isn't 10-15 clouds, distinct clouds lying there. They're like 10 raised to 6 to 10 raised to 8 clouds, which means it's basically just one continuum of clouds. In the case of the torus, we made the reverse assumption. We assumed that it is sort of like a blob of dust. Now we're asking, does the data support this assumption? So if the torus were continuous over the range of radii observed, one would expect substantially hotter dust emission in type 1 AGN than type 2 AGNs. Why is that? Okay, let me give you a hint. In which AGN will you be able to see the inner edge of the torus?
Type 1.
Type 1, that's absolutely right. So in the case of the type 1 AGN, is the spot where you will be able to see the inner edge, right? In the type 2 AGN, the inner part of the dusty torus, which is hot, right? You will not be able to see. So what will happen? Type 1 AGNs, one sees the hot inner wall, while in type 2 AGNs, one can only see the cooler dust at larger radii. But if you look at make observations of type 1 and type 2 AGN, this is not seen. In both cases, you're seeing both a mixture of hot dust and cold dust. This result and several others have led for the preference for clumpy torus models. So this is now a model for the torus. So there is a black hole, there is an inner radius, sublimation radius that defines the inner edge of the torus. But the torus itself is composed of clouds or dusty clouds, small dusty clouds, which have gaps between them. So whether you look at, when you look at it as a type 1 AGN, you of course see the hot inner dust. But even when you are looking at a type 2 AGN, some of the hot dust in the inner regions can also release photons which can escape to the observer. So, for example, this dust cloud, if it's going to be quite hot, it's close. If it emits a photon, that photon is able to reach us. So although it's nominally a type 2 kind of AGN, it can show a signal from hot dust. It of course shows signal from cold dust as well. And even in the type 1 AGN, of course, you see the central engine, the inner radius. So you will definitely see hot dust, but you can also see emission from these sort of lower temperature clouds, dust clouds that are located at a larger distance. So unlike the BLR, in the BLR, we merge distinct clouds into one big continuum. In the case of the torus, we have modified our picture and taken the dusty torus and split it up into smaller bits and pieces. Right. AGN type becomes a orientation dependent probability. So of course, the probability of seeing hot dust is higher in the case of type 1 AGN than type 2 AGN. And therefore, to explain the full NIR, mid-IR spectrum that one sees in type 2 AGN, one must also include NLR dust emission. So NLR also has some amount of dust, and a detailed treatment of the hot graphite dust, which is there in the near the inner walls of the torus. So a lot of measurements have been made. One can measure the Keplerian rotation, Keplerian velocities. They're of the order of 1,000 kilometers per second at the inner edge of the torus. So torus is rotating pretty quickly. For context, does anyone know what is the rotation speed, revolution speed of the Earth around the Sun?
It's around 220 kilometers per second.
No, it's about more like 30 kilometers per second.
On the sun.
That is the velocity of the sun around the center of our galaxy. I'm asking about the Earth going around the sun, right? So the Earth goes around the sun at about 30 kilometers per second. So this is much, much faster than that. And density of torus clumps are 10 raised to 5 to 10 raised to 7 particles per centimeter cube. Okay. Now we come to a revisit of the X-ray properties of AGN. Now, if you look at AGN, the highest temperature that one sees in the accretion disk, we've already looked at temperature profiles and so on. We said that the highest temperature you reach is about 10 raised to 5 Kelvin. In one of the previous lectures, we tried to compute at what wavelength would this emission peak. And we found that that is about 50 angstroms. But that is in the far UV band. X-rays are at much higher energies. So, but we have been observing AGN for many years, and we have detected soft X-ray emission and soft X-ray emission we have detected from of the order of 100,000 AGN now. And hard X-ray emission we have detected in some AGN reaching up to energies of 150 kilo electron volt and beyond. So the question is, how can you possibly have emission from the accretion disk with such high energies? Yes, thoughts?
So it can be due to non-thermal processes.
Yes, absolutely right. So what kind of non-thermal processes do you know where X-ray emission happens?
Synchrotron.
You mean Synchrotron emission, yes, that is one possibility. What else?
Bremsstrahlung.
Bremsstrahlung is another possibility. What is anything else?
Inverse Compton.
Inverse Compton scattering. That is a third process that can create very, very high energy photons. Now, in the case, so for example, we have encountered a similar situation in the case of the sun, right? If you look at the sun, you know what its temperature is. You know what it's a thermal black body. It should not have any radio emission or X-ray emission at all, because it peaks at 6,000 Kelvin or so. For black body radiation, you will find that if its width is typically a factor of 2. So if you take a star like the sun, most of its energy is emitted between, say, 4,000 angstroms and 8,000 angstroms or 9,000 angstroms, something like that. You don't expect the sun to emit in X-ray and radio, but we find that the sun is a very strong emitter in both X-ray and radio. And we came up with an explanation that, yes, it emits because it's non-thermal in nature. So your arguments are all correct. It is due to non-thermal emission that these X-rays must be emitted. There is no way that the accretion disk itself can create the kind of photons like these 150 keV photons that we are seeing in large numbers from X-ray AGN. So models have been proposed. So the idea is that there is, just like there is the solar corona, there is a magnetized disk corona, and that corona exhibits several of the same kind of features that the solar corona exhibits, except that it is very close to the supermassive black hole. The temperature of the disk is 10⁵ Kelvin, unlike few times 10⁵ Kelvin at the surface of the sun. But of course, the disk becomes cooler outside, and in the outer parts of the accretion disk, definitely we have temperatures like the temperature of the sun. Now, there are a lot of models that have been proposed for the X-ray emission. All of them involve magnetism in some form, and that requires you to have a magnetized disk. We don't have a problem with that at all, because we are also invoking a magnetized disk in order to explain the jet emission from AGN. So definitely there is this. So the corona therefore will act as a source of synchrotron X-ray emission, right? Maybe Bremsstrahlung will be hard unless the densities are high enough, but there will be some amount of free radiation, the thermal Bremsstrahlung. But there could also be inverse Compton scattering of the photons that are emerging from the disk, because remember, because of this heating of the corona, the temperature of the corona will be very high, 10⁷ Kelvin kind of thing, just like for the sun. And therefore, you could also have some amount of inverse Compton scattering of the photons, optical UV photons that are emerging from the disk. But we've in astrophysics, so I made this sort of slightly rude remark, but I think it's sort of true that in astronomy you will find that if you don't understand what's going on, you try to attribute it to dark matter, dark energy, or magnetism. And magnetism, of course, we know is real, but because it is so difficult to measure directly, it becomes very difficult to distinguish between various models of magnetism. So there are two families of models here also. Some people say that the entire disk is magnetized and the coronal disk exists quite far out. Some people say no, the coronal jet exists only quite close to the supermassive black hole in the regions, in the same regions where the flux tubes for the radio synchrotron emission emerge from very close to the black. Now we have no observational way of really distinguishing between the two models, but we can infer from the X-ray observations a few things about the corona. We believe that the temperature of the corona is very high, up to 10⁸ Kelvin. And we know, or we believe, that the corona Compton upscatters the EUV optical photons from the disk. The corona is magnetically heated with a mechanism similar to what operates in the sun. So there are magnetic flares which are being created continuously from the accretion disk. And those are the ones that really heat up the corona. The corona has a temperature of about 150 keV, beyond which an exponential cutoff is observed. Okay. Its nature, I've already remarked on this. There is a lot that we can that we need to learn about the corona's properties. We know it must exist because we are seeing a lot of X-ray photons emerging out of AGN. But whether it is sandwiching the disk everywhere, whether it only is present near the base of the jet, all of these remain unanswered questions, which are now increasingly, now meaning in the last 10-15 years, have been increasingly tackled, not just with observations and theory, but with magnetohydrodynamic simulation. So just like there are a lot of people who do MHD simulations of the radio jet. There are people who do MHD simulations of the accretion disk. And it's a very hot plasma, and the same problems that plague the properties of jets also affect the properties of the accretion disk. So a lot of work is being done via numerical simulations to solve the magnetohydrodynamic equations in a purely numerical way on a computer. Right. So this is a schematic view of emission from the disk and the corona. So the disk produces the bulk of the thermal emission, which sort of ends at a few hundred electron volt. It can't even reach a kilo electron volt because the temperature of the accretion disk cannot go beyond 10⁵. Beyond that, the hot corona takes over, and then at some, so it dominates the soft X-ray and hard X-ray emission till about 150 kilo electron volt. It's pretty strong, and then it sort of gets exponentially cut off. So this is our sort of view of the broad spectral emission from AGN, explained as a combination of UV emission coming from the accretion disk and X-ray emission coming from the disk corona. In addition to this, in some cases, a soft X-ray excess is seen. So in some AGN, you model the AGN emission. See, over here or here, everywhere, we model AGN as a power law, right, of different slopes depending on the temperatures and so on. So here, if you model the power law and take it out, even then there are data points at the sort of sub keV kind of levels, where suddenly you see a significant amount of soft X-ray excess. Now, what may be causing that? It has a approximately black body spectral form below about 1.5 keV. So it seems to be too hot and too variable to be from the standard accretion disk. So you can't say that, okay, this is just emission from the innermost part of the accretion disk. No, it is more energetic than that, and too variable. And it's likely a combination of disk emission at the lowest energies plus a cool Compton scattered component and disk reflection. So there is some amount of emission of the low energy photons, which is Compton upscattered, and some of it may be reflection from the disk. Now we'll go to really another view of what we see, which includes now the soft X-ray. So the soft X-ray excess is there below 1.5 keV. Beyond, in the soft X-ray band, it's mostly a power law, right? It's mostly a power law because it's just thermal emission from the, non-thermal emission from the hot corona. Now, there is also the ion K line, which pumps in between it's at about 5.65 kilo electron volt. We looked at the asymmetry and so on. Now, this ion K line is extremely strong, and it's often seen in X-ray AGN, and it is, of course, asymmetric, and also is indicative of the high metallicity of the AGN. Then there is a high energy cutoff. Now, the exact nature of the high energy cutoff is not known, right? That is something that is also being worked on, but there are a lot of complicated effects that have to be dealt with there, because remember, like for the iron line, everything that you do here has to take into account special relativistic effects. So there is Doppler boosting and things like that. But there is also general relativistic effects, which lead to some kind of gravitational redshift, and also distortions in the photon flux that is emitted. Okay, so I think I've forgotten to make some more slides. So just give me a minute. I'll just stop sharing for a second and load some more slides. Okay. So Okay, so what I would like to do in the next 10 minutes or so is to spend some time on just one slide, which is here. I'm sharing it. Yeah. Okay, are you able to see my slide?
Yes, sir.
Yeah. So what we will do now is just sort of review what we have learned about AGN properties and how they can be explained in the context of AGN unification. So we'll go sort of point by point. And what I would like one of you to state for each point is what data is supporting the unification scheme for every sort of observation that is made. So I've given you as a starting point the first one, which is if you look at the AGN, they have a fairly strong UV to X-ray continuum. And we've now explained it as a black body from the accretion disk plus some non-thermal emission from the disk corona are sufficient to explain the strong UV to X-ray emission that we see. So now we'll go point by point and just try to understand what observations support I mean, how these observations can be explained by the unified scheme. So rapid variability in blazars, no emission lines. What does that tell us? How is the unified scheme able to explain this? Come on. Blazars show rapid variability. What does that indicate? Why is it variable?
In case of blazars, we are looking at the jets.
Yeah, we are looking
And
just down the jets, correct.
Small variation in angle and because of variability in velocities in different part of the jets.
Yes.
Can
Also, there
cause
can be
variation.
shock reacceleration in the jet itself, right? So suddenly the flux may go up. So there is a geometrical effect from special relativity, the Doppler boosting, but there is also the effect of inherent variability in the jet flux itself or the jet luminosity. Why no emission lines? The emission lines are actually there. They're just relatively drowned by the very strong emission that is seen. So where are the emission lines coming from? From the clouds, right? Broadline emission lines from the broadline clouds and narrow emission lines from the narrow line region, correct? Is that Doppler boosted?
Yes.
No.
No, right? Because the Doppler boosting only happens for the jet. Because the jet is moving towards us at the speed of light. The broadline regions are not moving at the speed of light. Therefore, there's no Doppler boosting of the broadline or the narrow line region emission. So the emission lines are still there. They're as strong as they would otherwise be, but the continuum has been boosted by a very large factor. So the lines get sort of hidden in the thing. And so if you do very careful continuum subtraction of a blazar spectrum, you'll see the lines. But it's just that it looks like noise. It looks like very small variations on the lines. Okay. Yeah, go ahead.
The boosted continuum, we are talking about the radio frequencies, right?
No, the blazar
all-
also, the optical gets boosted, not just the radio, right? Because if the jet is coming towards you, the optical jet gets boosted. And as we saw, the boosting factors due to Doppler boosting, if it's coming straight at you, can easily be factors of thousands. So it is synchrotron emission, but it is not radio synchrotron, it's optical synchrotron emission. Right. Gamma ray emission commonly seen in blazars. This is again a purely special relativistic effect, because what happens is that the frequency of the photon as seen by you, if it is moving towards you at the speed of light, is going to be increased, right? You'll see X-ray photon, if it is coming, you'll see easily as a gamma ray photon. So it is commonly seen because again, you are seeing down the jet. Strong broad emission lines in many AGN, they are explained as emission from the broad line region. The narrow emission lines are we've seen as emission from a much larger region, the narrow line region, which produces the narrow emission lines. Strong jet emission in radio. Right? This is a little bit of halfway game, because we definitely don't know for sure why only a fraction of AGN show jets. Now, we have some inkling. We have seen that there are two modes in which a quasar can operate. One is a radiatively efficient mode, which is called as the quasar mode. In that case, no jets are produced. The quasar is very, very luminous. There is feedback not from the jets, but only from the luminous AGN at the same time. But at much lower accretion rates, the process becomes radiatively inefficient. And in cases where the spin of the black hole and the spin of the accretion disk are very high, in such situations, we expect that sort of magnetic pinning in the accretion disk will lead to channeling of particles away from the black hole in the form of jets. So strong emission in radio, being there, not being there, is not a pure consequence of the AGN unification scheme. It is a consequence of the AGN operating in the radio mode as well as the quasar mode, depending upon the black hole mass, but also depending upon, more importantly, on the accretion rate. We see steep spectrum emission in radio lobes. How do you explain that?
So the steep spectrum in emission of radio lobes is due to large fraction of high energy electrons coming down instantly and emitting in recombination is much more.
Yes. Yeah. And recombination timescales are very short. So they lose energy, right? And they emit the higher energy electrons, emit radiation, more synchrotron radiation than the low energy ones. And that leads to a steepening of the spectrum. One-sided jets in most quasars, again, quite consistent with the unification scheme, because we can explain that in terms of Doppler boosting, right? Jets aligned on all length scales probed. This indicates that the origin of the jet must be very, very close to the black hole. And this is exactly what is predicted by the Blandford-Janek model. And so it's not a problem at all explaining this. AGN are more common at z equal to 2 than they are today. That's definitely true. And we explained this strong evolution of the AGN luminosity function by claiming that mergers were more common at high redshifts. as a result of which the AGN were more common, because that there were various ways of driving gas into the central region where it could be accreted onto the black hole and help grow the mass of the black hole rapidly, but also help start emission through an accretion disk. Superluminal motion, we explained that quite simply by jets that are moving at close to the speed of light. Need not be very close. Even you can get superluminal motion even with jets traveling at 0.2 C or 0.3 C. Zero proper motions. Okay, this of course then require the AGN scheme, but this in the early days used to be used as an argument that these AGN, especially the quasars which were discovered first, are not part of the galaxy. So for the first 3-4 years, people were trying to explain the quasar redshift in terms of gravitational redshift and things like that. But those explanations faded away, because if these quasars were actually within our galaxy, there was maybe some kind of binary stars or whatever, then they would be seen to move. And no quasar has ever been seen to move. And they have zero proper motions. And therefore, what people have done is that they've defined by using the positions of radio sources, point sources, determined extremely accurately with VLBI observations and other techniques, we get the very accurate position of a number of quasars, and that allows us to define a positional grid. So you define the position of an object in a frame which is called as the ICRS frame, which is a set of radio sources that have very accurately determined positions and have been tracked for many years, sometimes many decades, to verify that their relative separation doesn't change, which means they don't move relative to each other at all. So that gives us a fixed frame. In the old days, when we didn't know too much about proper motions, we used the stars to define the coordinate system on the sky. But now we know that the stars are moving around, especially with the data from Gaia. We know how much they're moving around, and therefore we've stopped using stars to define coordinate systems. We're using distant quasars. So in that context, the zero proper motion idea is also quite important. Okay, so we will stop now, and in the last lecture, I would like to cover a few topics that have not received the kind of attention that they deserve. I'll talk, for example, about gamma ray astronomy, as well as I'll talk a little bit about particles, cosmic rays that emanate from AGN, and how they can be observed on Earth, and how one can learn about AGN, not just with photons, but one can learn a little bit more about them using particles that travel to us from them. And then I will just cover 2 or 3 sort of interesting ideas about AGN, and how in the coming decade or so, AGN science could be revolutionized by the discovery of a very large number of type 2 AGN, as well as type 1 AGN from large area synoptic surveys. So that's where we will end. So I'm going to send out an email now saying that our seminar is fixed for the 29th. Some of you have responded to me giving your choice of paper. So as soon as I hear from you, I'm putting your name on the same web page. So against the paper, if you see your name listed, that means nominally you're there. I got 2. I've got one clash already between the 4 people who've responded to me. There is a clash for a paper. Two guys want to work on massive AGN as discovered from the LOTS survey. So we'll resolve it. Don't worry about it. Within the next 2-3 days, we'll resolve it. But really keep in mind by Friday, please send me an email which paper you want to select. And those of you who already sent me email, please check the web page, and there you will find your name listed against the paper. And I hope we can converge on that by Friday evening, and by the weekend we will resolve the conflicts. Okay. So any questions?
Hello, sir.
Yeah.
Sir, in the by the zero proper motion, it is meant that all the redshift that we observe from the AGNs is purely due to the expansion of universe.
Yes.
Rather than the relative velocity. So I guess there is no way to know whether the redshift is from the relative motion or from the expansion. So how do we exactly know that there are zero proper motions at the AGN?
No, you measure the proper motions irrespective of the redshift, correct? You don't have to assume that the redshift is cosmological to measure the proper motion. So the proper motion is not measured in parsec or milliparsec or whatever. It is measured in arc seconds, milli-arc seconds, micro-arc seconds. So the position of those objects on the sky doesn't change in terms of angular separation. We're not measuring the physical movement. Does that answer your question?
Yes, sir.
Yeah, so it's just an angular movement, and that's what Gaia does. It doesn't know how far the star is, but it will tell you that it is moving at so many micro-arc second per year. Yeah, but in the 60s, there was a lot of debate whether the redshift is cosmological or not. By cosmological redshift, one means that it's caused by the expansion of the universe. There were for a few years a number of attempts made to explain the quasar phenomenon by placing the objects within our galaxy, because that would have solved a lot of other problems, including why they are so energetic over so many frequencies. So if the quasars were, for example, accreting stars, binary stars, the energetics, everything is something that can be, doesn't require anything exotic to understand. But once by the late 60s, when it was established that the gravitational potential energy is sufficient to power the AGN, many of these arguments fell to the side. And then, of course, some years later, people found the quasar sitting in the center of a galaxy. So nothing more to say after that. Okay. Okay, so I'll